various aspects of the complexity theory. And then in the last class, we started the quantum information a bit. Although there is a separate entire module on this complexity, the communication part in QT-06. We have seen like details of the quantum communications, digital communication information theory, and here it's just an overview. You are not getting the entire theory. So I today I'll be taking some portions on the quantum information theory and some little bit on the communication and complexity as well. And so yesterday where we left, I'll start from there. I'll be taking some 30 minutes to 45 minutes on complexity theory. Then in the second 45-minute session, we'll be coming back to the information theory part, especially the quantum communication part as per syllabus. And then I'll take questions. As many questions you have, I'll give at least 15 minutes to put all your questions. So please feel free to put your questions in the chat box. I'll be taking all the questions while starting the session. So yesterday we talked about three particular class complexity. I mean, in terms of the Turing machine. So one particular part is the DTM, deterministic Turing machine. The second part we talked about the probabilistic Turing machine, and also we introduced the quantum Turing machine. Now all these things has a lot of relation. This is just not the theory. It has a lot of when suppose in the last session you have seen that probably Janani was talking about this the source algorithm, right? And she was talking about why this algorithm is giving you some complexity of order of n to the power 3 approximately. So so why it is n to the power 3, and whereas just for the RSA encryption, right? So if you are using the C-field like algorithm, the best known classical algorithm, you have some the like finding the prime factors of a big number will take like exponential complexity with the order of n. And because the prime factor, basically computing the prime factors of a big number is exponentially hard, so you cannot break this RSA key with classical if this n is quite high. So now we will quantify what class of complexity this is, why, how much hard complexity, I mean class wise, some of these algorithms in quantum. So, and for that actually, computer theorist designed a particular Turing machine called the QTM. And we have seen like several properties of the QTM in the last class. So I'll define something called a quantum circuit first. What is a quantum circuit? So this is just not, I'm not just writing a program, but we're defining a quantum circuit in the language of the Turing machine, okay, as a computational model, basically. So like you have learned the finite machine model, right? So normal DTM, discrete, like deterministic Turing machine model. Similarly, there is a model, language model called the circuit model, quantum circuit model. The definition is a quantum circuit of qubit size n. And when I say qubit size n, so there is a notion of space complexity. There is a notion of space complexity. I mean, this is not the space complexity, but there is a notion of the space complexity. A quantum circuit of qubit size n is a sequence of unitary gates. Unitary gates. Now you can ask question why it is unitary gates, right? So like how you derive the like Schrodinger equation and all. So in QT-0001, this is well described. If there is a repetition in course, I'll again repeat maybe, okay? Or you can revisit the courses available on YouTube. So A quantum circuit of the size n number of qubits is a sequence of unitary gates. Say the gates are U1, U2 to UN, each acting on at most k qubits, where your k is say less than equals to n. And when I say these unitary gates are acting, right? So there actually is the notion of time. Time complexity, okay, notion of time. So typically the circuit is followed by measurements to get the classical information back. So what did I tell is that suppose you are just designing an algorithm and you consider say 5 qubits, all starting with gate 0 state. Now, so this is the part where you first initialize the circuit. This is the input part of the circuit. Now you need to encode your information. In order to encode your information, basically you apply certain gates, right? And there are two types of wiring. One of this wiring is just a direct wire, right? Now on this wire, first you apply the say certain gate. Say you apply a Hadamard gate, or you apply a R theta gate, certain rotation gates, or say Pauli X gate, whatever gate you want to apply, you can apply. So a circuit is basically a set of qubits where you apply a set of unitary operators. Now that unitary operator can act on a particular single qubit, or they can act on multiple qubits. For example, it's a 4 qubit gate. It can be something like this, or it can be simply C naught 2 qubit gate, right? You can decompose a multi-qubit gate into single qubit and 2 qubit. Yeah, thank you everyone. Good evening. So these are the sets of 1 qubit and 2 qubit gate. It can be multi-qubit as well. For example, the Toffoli gate, the Fredkin gate. There are different types of gates, right? Multi-qubit gates are there. Now the question is, and after the after all application of all such unitary, say U1, U2, U3, set of thing, and then basically you do the measurement operator, right? You do the measurement, and after the measurement, whatever information you get, you basically denote them by 2 words. Okay, these 2 words means the classical information. So this double notation signifies classical information, classical register basically. This is the set of qubits, so they basically denoted by single wiring, and these are the quantum registers. Quantum register. Okay. So where basically you encode your informations, right? So this is a quantum circuit. Now, along this, basically, from if you look at the circuit part from top to bottom, you have a sequence of quantum gates that you say, okay, I have n number of qubits, right? Now these qubits are physical, right? Physical means either you have photons or you have ions, like the in ion trap technology, in photonic technology, or you have like artificial atoms in superconducting technology like IBM and Google's machine. In ion trap technology, they are ions. In photonic chips, like there is other phenomena also, like for example, the Microsoft technology on the um, so topological qubits, for example. So they can be of different type, right? But they are physical source of informations, what we call the quantum registers. And as when you design an algorithm and you define, okay, if I want to run a particular problem, and that particular problem, I need to have poly n number of qubits. That means you have a space complexity of poly n, right? So it's an basically polynomial in number of qubits, your particular problem, right? Source algorithm is one of the algorithms in quantum. I'll basically explain a number of quantum algorithms and analyze their complexity. So we need to see, if I want to solve a problem on a quantum computer, I am not taking the exponential number of qubits. That is first question. Then there is no advantage at all. Okay. So this is one part. And this particular has the notion of space complexity. This is not space complexity, but it has notion of space complexity. Okay. This is equivalent to space complexity in the circuit phenomena, circuit model of computation. Okay. And if you see from, say, if you see from this left to right, so first we have seen from top to bottom approach in the circuit, where we have certain number of qubits. Often we represent by q0, q1, q2, so on up to qn, n number of qubits, n minus 1 basically. Now from left to right, basically, in a particular, like you select a particular area, what we call a layer, say layer 1, layer 2, like that. In a particular layer, you can apply certain number of quantum gates. And because they are unitary matrices, say 2 cross 2, 2 cross 2, 2 cross 2, and suppose there is nothing, means identity matrix 2 cross 2, right? Because each quantum information has 2 cross 1 vector dimension, right? So the corresponding operators matrix should be 2 cross 2 at least, right? If you are applying, say for example, C0 gate, you have basically taken 2 qubits, right? So the tensor product will be 4 cross 1 dimension. Hence the C0 matrix should be 4 cross 4 matrix, right? So in general, if I have say I have n qubit, n number of qubit, and I apply a particular operator. Okay, so then basically this particular operator should have 2 to the power n cross 2 to the power n matrix dimension, right? Because this particular n qubit has 2 to the power n cross 1 is the vector dimension. So the matrix or operator dimension will be 2 to the power n cross 2 to the power n, right? Now, if you go from left to right, every time you are basically applying certain gates, right? And that gates means in the physical hardware, what it is happening. Suppose you say, for example, in superconducting qubit, right? You have a ground state and you have certain say excited state, right? Say this is gate 0 and gate 1 is the like convention, right? Or in a particular photonic qubit system, you take two particular photon, one in the basically horizontal polarization, another one say vertical polarizations, right? As the basis of your information, this is suppose gate 0 and this is suppose gate 1 in the photonic, right? And this is in the superconducting, for example. So you may have one particular atom you take for one qubit representation, and another particular artificial atom you can take as your another particular qubit 1, q0, and this is q1, right? Similarly, you take the polarization of basically photons, right, in the photonic chip. Or in the ion trap technology, suppose you have two particular ion, one particular ion has a plus spin or the plus half spin, and another may have the opposite spin, right? Say this is plus and this is minus, or the vice versa, whatever it is. And they can basically rotate in a plane. Okay, they can have molecular spin as well, may or may not have the molecular spin other than their own orbital spin, right? So you can select those many qubits. We'll maybe in the next QT most likely 10. I have some solid state like I have some class on the basic quantum information, and that is because belonging to the solid state physics. So I'll cover these things in a bit more detailed. Uh, Now you are applying, basically you created an information between superposition of this and this qubit. Um, and you can create a superpositions between these photons and these photons, or in the basically two particular ions in the ion trap technology. Okay, these three different technology of quantum. So what you are effectively doing, you are basically for a particular Hadamard gate application, for example, Hadamard or the C naught or the Pauli naught or C naught, right? Or the T gate or the phase gate. There are different kind of operations you can do because they are matrices. You are applying to the vectors. You can do here, you can do here, you can do here, right? This kind of operations you are doing. Now, by doing these operations, in this particular case, what you are doing, superconducting, you are basically injecting certain pulse signal. Pulse signal. Now, each signal has a particular, if it is a pulse signal, so pulse means what? Pulse means it has a very less time with this is delta t, but it has a high amplitude, right? A. So for a very shorter duration, what you are doing, you are creating a signal with very high amplitude, right? In order to break its, for example, a particular state, say it is Ket0, and you want to make it to Ket1, right? By applying, yesterday we have seen like by doing the annihilation operation or creation operations using the singleton operator, or in fact you can use simply a Pauli X gate, sigma X, right? So for Pauli X, when basically your information is here and you want to represent your information fully in the Ket1 state here, right? So you have to basically apply this kind of pulse signals, right? In photonics, they have a different kind of technology, like whether they use the beam splitter, etc., etc. In the spin, like ion trap, also they have a different kind of technology to implement these kinds of gate. Now, what I'm telling this because this delta t is important, right? Now, this delta t, because you created an information here, suppose you have like a particular setup and you are basically interacting this particular quantum gate implementation on that particular quantum system, right? Superconducting system. So even if you have created certain state, for example, A Ket0 plus B Ket1 was your initial state, and then basically you are applying certain unitary gate here, right? That means it is basically affecting your A, it is affecting your B, this particular quantity transpose, right? So these, how much you are interacting this within coherence time or not, those things are important. So this delta t has a time notion. Why I am basically uh, talking in all these physics details in this particular complexity class, it is important because I said if I apply say n number of gates, that means it has taken lot of time. So the concept from left to right is related about the time complexity. So the question is not your algorithm is taking how many qubits, but also your algorithm is taking how much time, right? So that means how much time is related to number of gates. So that's why in quantum research papers, you will see people often study all this stuff using the gate complexity. Even my entire PhD thesis was only on this gate complexity aspects of certain algorithms. Okay. Now, the question is not only about the number of gates, but also in a particular layer, how many layers are there? And in a particular layer, how many quantum gates that you are using? So there is a more concept, there is a more deeper concept called a circuit depth. Circuit depth. That means you designed an algorithm. How depth your algorithm is means how much layer you have used for implementing those pulse signals, different types of pulse signals, microwave pulse signals, in order to apply all these unitary gates, right, to your physical qubit. So what we understood is that a circuit model is a set of qubit, right? And this sets of qubits, say q0, q1, q2, dot, 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 q n minus 1. So this is the concept of space complexity along this top to bottom approach. And from left to right, how many quantum gates you are using, right? So this is the notion of time. Now this entire, you can solve any problem on quantum computer, suppose, but suppose you are taking t amount of time and each physical qubit has an overall coherence time, say tc, within which basically they hold the quantum informations with affordable accuracy or affordable reliability, if your total time taken by the entire gate implementations is greater than TC, then after measurement, whatever classical information you get, right, C, may not be meaningful. May not be meaningful. That means huge error. Right. So the overall budget, this is called a budget, gate budget. Budget should be as such that is matching with the fidelity of the qubit. So in typically they have certain coherence times equation T1, T2. These are different time constant in the equations. They are related. I'm not going in that physics detail part, but computationally, for example, on current IBM machine, you have a 5,000 number of 2-qubit gates. 2-qubit gates are available, which has, like, if you are using less than 5,000 2-qubit gates, and we have 156 number of qubits. So this is the giving you notion of your space complexity, because you can at most do, suppose you have n number of qubits, you can at most create a quantum state of 2 to the power n. So that means 2 to the power 156, but actually you cannot use all the qubits. Suppose you are using 100 or 120 qubits out of the 156, because other qubits are used for other purposes like error mitigation and other stuff, because of the noise eliminations, mitigation, etc. So you can create 2 to the power 100 particular state. So that means 2 to the power 100 state vector you can create. So you can create 2 to the power 100 cross 2 to the power 100 Hilbert space. This is the available space. Now, in that particular available space, what quantum operation you want to do, it should be supported by 5,000 maximum number of quantum gates, not more than that, because otherwise this condition will be violated. Total time taken by all gates may be greater than the TC, the coherence time of the qubits. So that means you may not have meaningful results from the quantum computer. That's why everybody is trying to increase the number of physical qubit, improving the quality of the physical qubit as well as, and also increasing the capacity of the number of gates operations onto it. Like, means the enhancing the time complexity aspects of the problem, like the gate complexity aspects of the problem, as well as the space complexity aspect of the problem. So this is the circuit model part. If you have any question, you can put it down. Now, we'll see one theorem called the Solovey-Kitaev theorem. So basically, Solovey gave the first theorem in 1995. And then there is an add-on, basically change of the theory or the upgradation of the theory by Kitaev in 1997. So they together known as the Solovey-Kitaev theorem. There is one question, why 100? It's only 156 qubit. Okay, creating a single qubit is a huge engineering work. Mathematically, it looks beautiful, but creating a qubit and holding its coherence time in the cryogenic setup is a huge work. Okay, you can just think about, for example, you want to create a 8 cross, for example, say 8 cross 8, like the DFT circuit, a discrete Fourier transform circuit. And you just imagine, just only create this 8 cross 8, this DFT matrix. How many number of AND gate, OR gate, NOT gate you consider in the classical computation? Even on a particular AND gate, how many basically flip-flops are used? In a particular flip-flop, how much transistors are accumulated there, right? Digital logic and all this. So you can think, I'm not telling about the exact relationship, but I'm telling about the difficulty of the engineering challenge. So 100 qubit is not less, it's a huge number, right? Because if you see the classical computer, your HPC, high performance computer, even if you look at, currently it works on maximum exascale computation. So exascale computation means 10 to the power 18 floating operation per second, flops, right? So means it can maximum does 10 to the power 18 operations per second, right? Now this is equivalent to 2 to the power 60, right? So if you just compare this classical versus quantum, you cannot compare the apple versus orange, but somehow just we are doing it. If you compare in this way, it is 2 to the power 60. That means if you have good 60 qubit, good quality 60 qubits, they are capable enough to do all the tasks particular HPC does equivalently. I mean, you cannot solve every problem on a quantum computer, but the subset of problem that you can do on a quantum computer and you can do on the HPC. Now the power of HPC 10 to the power 18 flops, right, is equivalent to 2 to the power 60. That means it's a 60 qubit thing. So you have many problems. I'm not discussing those problems today, which you can solve on a quantum computer beyond 60 qubits. That means if they are good quality qubits, so there are problems you can solve on a quantum computer, which may not be actually solved on a classical problem. That is understood. But why you are considering 156 qubit complexity? Okay, so 156 is the number of qubit in our IBM processor known as Heron processor, Heron R2, R3. These are processor names, and this is the maximum number of qubit available on Earth. Okay, on the current superconducting technology. I mean, there are like modularity thing, like people are basically joining multiple small chips together to make it bigger. But on a single chip, single basically lattice, the maximum number of qubit available is 156 with IBM. All right. And Google also released towards last year, and Willow processor that has, I think, 108 number of qubits. Okay, so these are industry numbers only. Okay. Fine. Now, what this Solovey-Kitaev theorem states? So this is a bit tricky mathematics. I'll try to explain as much as possible. And then if you have stuck, you can visit those aspects in Google, or many LLMs are there. You can chat with them. There is a constant. I'll explain. There is a constant C such that any G, and G is basically a finite set of elements in SU2. Any theoretical quantum computing paper, you will see this notation SU2, super unitary operator of 2 cross 2 dimension. Okay, containing, for example, the Pauli operators. Okay, containing its own inverse. What does it means? If there is an element G which belongs to the set G, capital G, and also there is an element, its inverse G inverse, that if that also belongs to the set capital G, if that is the situation, that means there is a constant C and there is a particular set such that any particular set G which has this particular property, and let's take a small number epsilon greater than 0, then this theory says that any unitary operator that belongs to the super unitary 2 SU2, there is a sequence S of gates, quantum gates, from G of length order of log to the power constant C 1 by epsilon up to epsilon error. Okay, such that norm of, you can take operator norm of S minus U less than epsilon. So we say S is an approximation, or S approximates U to operator norm. What does this particular theorem says? I'll come. Okay, just let me write the equation. Alternate definition is that, or alternatively, the theorem says that the overhead of computing, with a discrete universal gate set. This is important. What do you mean by universal gate set? We'll come back in quantum. Like in classical, typically the AND gate and NOT gate together called the universal classical gate set. Some books people consider NOT, NOR, and NAND as a universal gate. In quantum, we have certain quantum gates. I'll come. What are the universal gate set? Okay. So the overhead of computing with a discrete universal gate set is polylogarithmic. What does it mean is that suppose you have certain signal, okay, S of t, right? And you want to do Laplace transform on that particular signal. Okay, you want to do the analyze the control system problem, for example, right? Finding the fault in a particular system from the transient response, right? Or it can be like in image processing, basically identifying noise in the images and eliminate the noise, right? So there might be multiple applications, right? And basically S of t to S of say sigma. This is what you want to do, right? And you have an encoded problem in the qubits, say Q0, Q1 to up to Qn, right? For the Laplace transform, suppose you have an unitary U such that it gives you in the initial state, that is the ket st, and this particular state should be ket a sigma, right? And after doing the measurement, basically you have a notion how these measured result probabilities, right? Probabilities, how they are related with the Laplace coefficients, for example, right? The question is, this is the ideal operator for Laplace transform. Now you may not have like a direct mathematical operator that you can simply multiply on the qubit and you will get the result. That may not be the case. Suppose you design alternatively another operator S, which is basically, for example, it's a tensor product of several basically gate, right? Tensor, so it's a product sum. So you can write in this way, sum of say AI pi, right, over I, where AI is certain constant and pi are certain basically Pauli string, right? This may be 2-qubit Pauli or the product of Pauli gates. That means this can look like this. For example, it can look like this. A ring structure entanglement pattern, for example. Say you have, this is called the hardware efficient answer in chemistry. So RZ, yeah, you can parameterize with theta, and these are C0 and C0. So I have taken two C0 gates, and then basically I have taken a parameterized Pauli G gate, right? Pauli G parameterized by theta, right? This is called the RZ theta gate. Okay. So you can have many such small circuit, and the overall representation of the circuit is basically, instead of you create some S, but this S is prepared as such that S minus U are the S is very close to U. That means S is an approximation of U, such that S minus U is basically less than some epsilon. The difference is less, the norm difference is less, right? So we say that we have an approximate operator S. Approximate operator S to U. Okay, where S is efficiently represented using the universal quantum gate set. Okay, so this is the and Solovey-Kitaev theorem says that you can make it in the polylogarithmic complexity. Okay, now I have used certain mathematical terms. Okay, so that is SU2, and I have to define this term. Although I mean, when I will be defining these terms, every time I'll bring some new mathematical terms, which may not be easy to define each term because it's a recursive thing. But in general, if you are interested, you can look at these things. These are interesting, but quite deep. So what is SU2, or in general, we called spatial unitary group or super unitary group, spatial unitary group, SU. Of course, for any unitary U star U equals to identity, or U star equals to identity if U is an unitary matrix. In general, this particular definition together can be written as U star equals to U inverse. This is the definition of unitary matrix. Okay. Now I am defining something special, some special version of the unitary matrix, means they have some special properties, right? This spatial unitary group basically denoted by SU of degree n, denoted by SUN operator. They are basically is the Lie group. So there is something called Lie algebra and Lie group. So I'm not going to that direction because of lack of time. So the spatial unitary group of degree n denoted by SUN is the Lie group of n cross n unitary matrices with determinant determinant 1. Okay. If you throw some light on the engineering challenges, okay, I'll talk this engineering challenges part in the next QT10. There is I will be taking 2 to 3 class on these basic quantum, how the qubit operates, basic quantum information, and I'll talk this part. Will there be SU3? Maybe if you have n equals to 3, you can have basically n equals to 3. But in general, we use the SU2. Basically, that goes with the dimensionality of the qubits easily. So SU2, SU4, these are some operators like SU2 to the power n in general. Extend the date till tonight for quiz 3. Okay. So what this theorem says is that for a single qubit gate, the SU2, they have this structure like the matrices can be of this particular thing, A minus B star and B alpha stars, right? So if you have matrices of this particular orientation, for example, the Pauli Y operator, sigma Y, right? 0, minus I, and 0, right? If you do the like basically if you look at these things, for example, I star, right? So so basically then it will be minus I, right? So this has this particular structure like alpha minus beta star and beta alpha star, right? So these are basically SU2 groups. All the Pauli basically matrices are of the SU2, where alpha and beta may be any complex number C, and alpha square plus beta square equals to 1. So this is the property for SU2 groups. Okay. Now, unitary matrices of 2 cross 2, unitary 2 cross 2 matrix they typically differ by, they only differ by global phase shift. Okay. And every matrix M that belongs to SU2 can be represented as so those who are facing bit difficulty in understanding, because you are taking this course as the first course, you may repeat the QT-00 to QT-056 at least, to have the basic background on the quantum computing. Because otherwise, if I repeat again what is KT0, KT1 and all these stuffs here again, or this stuff, basic mathematical stuff, maybe others like who are attending from QT1, they will feel boring. Now, what I'm saying, every matrix M in SU2 can be represented as M equals to Rz of alpha, Ry of theta, and Rz of beta. This is basically decomposition. Okay. Any SU2 gate you can decompose this way, in Pauli Y and Z type, right? With parameter alpha, beta, and theta. So I was talking about universal gate. Right. So in classical, like typically we have the NOT gate plus, if you have NOT and AND gate, you can design any logic, right? For it classically, right? So in quantum, you have typically various universal set of gates. For example, standard one is the Hadamard, T gate, and C naught gate. Okay. So T gate is a phase gate, C naught we know 2-qubit entangled gate. And Hadamard gate is a superposition gate that gives the informations of from 0 to plus, right? Or plus to 0, vice versa. So if you have a gate 0, if you apply Hadamard, it will be plus state. And if you apply another Hadamard, it will be again 0 state, because Hadamard is a reversible logic. Okay. All these things like T, C naught gate, all these are reversible logic only. Now, this is a standard universal gate set. Besides this, some people classify quantum gates as Clifford and non-Clifford. Clifford plus non-Clifford. This quantum like classification of quantum gates. So those quantum operators which follows the Clifford algebra, they call the Clifford gates, and those who does not obey the Clifford algebra call the non-Clifford gate. So okay, what is Clifford algebra and all? I'm not going to detail here. Maybe sometimes later we'll talk. But in general, the example we can take. So Clifford gates are typically your Hadamard gate, S gate. S gate has basically 90-degree phase, but T gate has 45-degree phase. The Hadamard S and C naught. And non-Clifford gate is basically T gate, right? So if you have these plus this, it will form a universal quantum gate set. In some computational model, R theta plus C naught is taken as universal gate set, that you can design any unitary operator using these two particular gate combinations. So these are several model in hardware specific, basically hardware specific gates, universal gates, which we called as hardware native basis gates. So there are gates like square root X, S, okay, H. So you can see a particular hardware, for example, IBM Kingston is a machine, right? Those who are using actually Kingston is a machine, you can see what are the basis gate set by which actually you can design the entire algorithm in terms of those basis gates. Now these basis gates are chosen because you need to create a very specific technology to implement this square root or AS or H in a particular topology, hardware topology. Actually, you have a native gate set which represent the entire logic actually, right? So this is not like any arbitrary gate. So when you design the entire quantum computer, you need to choose what are the affordable operations there without minimum error, minimum time, minimum cost, maximum reliability, right? So it highly depends on the engineering part of the generations, not just because of the mathematical parts. Okay. So this is the Solovay-Kitaev theorem part. And uh, let us talk about little bit on the more on the QTM, quantum Turing machine, and BQP, and then we'll go for QMA, quantum Marlin and Arthur complexity class. Okay. Phase gate is basically is a phase gate only. So typical structure of phase gate is like this: P theta equals to 1, 0, 0 e to the power I theta. Now this theta can be sometimes say 90°. This theta can be 45°, and accordingly this particular model will be changed, right? So this is the phase gate, and now some of the particular there are specific phase gates which are basically supported by hardware like S gate and T gate. So just if you just Google, you will get all the details. So I'm giving a break of 5 minutes. I'll just come back. If you have any question, you can put it here. I haven't started, that's why no audio. Give a break. Okay. So a quantum Turing machine is a Turing machine. A QTM is basically the Turing machine whose transition function. So because in the transition function we have seen like the in the definition of Turing machine, which was delta, right? So which transition function is an unitary operator. Unitary operator on a superposition of configurations. on a superposition of configurations. Unlike the probabilistic Turing machine, here the coefficients, like in the probabilistic Turing machine, the coefficients are non-negative numbers. But in the quantum Turing machine, the amplitudes are complex amplitudes, and they allow the interference, constructive and destructive interference, which is missing in the classical probabilistic Turing machine. That is only present in the quantum Turing machine, because that basically interfere the solution. Okay. So the BQP class, and and we'll actually see multiple examples of the BQP class. A language L we call as is in BQP bounded. What is BQP? BQP means bounded error quantum polynomial time. Quantum polynomial time. So what is polynomial concept we know, right? Like the time complexity or the space complexity polynomial. We also know the aspects of time and gate in quantum. We also know what is error, because we cannot, or we sometimes may not implement the exact unitary. We have a set of combination of gates that form the operator S, which is basically norm-bounded by epsilon. Now that particular error bound, right, in quantum, we have a particular class for that, complexity class for that, BQP. So we called the language L that is in BQP, if that particular error is polynomial order. If there exists a polynomial time, sometimes people call uniform. In some books, it is not present. Polynomial time family of quantum circuits, and we denote those circuit by Cn for n greater equals to 1, many circuits, so one or many circuits, where one circuit per input length such that each Cn uses poly n qubits and poly and polynomial in number of qubits and poly in number of gates. So if I design an algorithm, and if I take polynomial in the number of qubits and polynomial in the number of gates, then whatever error I incur, right, that belongs to the class of BQP, right, in the approximation versions, right? So poly and gates, for every input x of length n. So we say x belongs to the language L if the probability Cn circuit that takes the input x accepts is greater than 2/3, means I get the solution with probability at least 66.67% more than that. I say I say the basically input x belongs to L. I say x does not belongs to L if probability of giving the circuit with input x accepts has less than probability 1/3. Okay. So then we call this set of problems belongs to the BQP problem, like BQP set of problems. So they are basically quantum analog of BPP, right? Now you can ask question, why this 2/3 and 1/3? These are conventions that at what particular after what particular point you say, okay, you have a better solution. You designed an algorithm where your success rate is like from 0 to 100, right? So if you basically if you design an algorithm and you say I have 44.5% accuracy, okay, there is no meaning of designing that algorithm, because it is at least basically tossing a coin is better than your algorithm. Tossing a coin, because tossing a coin has roughly 50% probability. Then why I need an algorithm with this much complexity, this much basically effort, because I'm getting only accuracy 44.5%. So people, computer science people put a number 2/3 and 1/3. If it is greater than equals to like 2/3, I say, okay, this is the accepting solutions, right? And accordingly, they define this particular class called BPP, like bounded polynomial error problem. In quantum, they define something called BQP, right? But in some decision problem, we have seen that if it is just above 50%, I accept the solution, and just below 50%, I reject the solution, right? This may be the case in some problems. There people have strict class BP, that is called PP, like polynomial problem, right? PP particular class, okay? So polynomial error, that is not bounded polynomial problem, these are PP problem, okay? So that's why actually the entire the relationship looks like this, like the polynomial class belongs at the bottom, like it has the least complexity. Then BPP, this bounded polynomial error problem. Then BQP, bounded quantum polynomial error problem. Then PP, right, which has the looser definitions in terms of the 50% thing. And then all these are subset of P space. And P space is basically, that is the polynomial space complexity problem, which is a subset of exponential complexity problem. So this is the bigger relationship among all these classes. Okay. Now, let us discuss about some examples, and then we'll go back to the QMA class. This example you already have studied, right, in all the various classes. The first one is the Deutsch algorithm. I will not detail the algorithms, you already know. I'll just discuss about the complexity part. The first is the Deutsch algorithm. Deutsch sorry, Deutsch-Josa algorithm. The problem is, given a this is a BQP class problem. Given a black box, function f that takes values from 0, 1 bit string and produce the either 0 or 1, okay? It promised to be, given a black box function, this one, it promised to be either constant, like the, what do I mean by constant? That every time the output is same, like same output for all time. Or balanced. This is basically a like a toy model, like to understand the computational part. So DOIs basically designed this problem, like given a black box function, and it promised to be either producing constant result or balanced result. That means every time the machine produces the same result, right? Or balanced result means half of the time it basically maps to 0 and half of the time maps to 1. Exactly half inputs to be 0 and half to 1. So this is the problem. If I can create this particular machine, right? So classically, how many queries I need, right, for the Deutsch-Josa algorithm, like for to solve this kind of designing this kind of black box problem. So classical complexity is if you have n number of bits, Then it takes 2 to the power n minus 1 plus 1 queries to check are required in the deterministic case, basically. Now in quantum, actually, if you use the basically Deutsch algorithm, the quantum. Now this particular algorithm may not have any practical use cases, but it's a toy problem to understand the computational complexity advantage of the quantum algorithm. So it takes only one query to solve it. It takes only one query is required. So it is basically a promise problem in basically in computation. So you can see, like, if you have an n number of bits, so and you want to basically find this black box solution, like either the output is balanced or constant. It takes 2 power n, like order of 2 to the power n is the exponential complexity, and here only order of 1 is the required solutions in Deutsch social. Okay. So those who are interested, they can like see how to prepare the Deutsch Josa algorithm. So there will be one Z missing probably. The actual spelling will be JOZSA. Okay. So it's something like you start with the Ket0 state. I'm not explaining the algorithm, and then basically prepare a state like Ket0 all n, Ket0 1. Then you apply certain Hadamard gates to create the superposition state, like 1 by square root 2 to the power n sum over x get x tensor product of minus state. So there is a way how to do this. So I am not telling the algorithmic step, like computing and uncomputing part, and finally measure on all the basically 0th qubit basically to check whether the output is constant or not. So here you can check, like basically it will compute only one query complexity. The second one is the Grover's algorithm. Maybe sometime later when we'll be discussing about various algorithms, and you will put this question, why it is a single query question. I'm not this class, I'm not telling why answer, because every algorithm has a detailed explanation. We will take one class, but I'm telling the what kind of complexity it is. The Grover's algorithm, and the problem is given a black box function f from the text value from 0 1 bit string and produces the output either 0 or 1. Is basically a decision. This definition means a decision problem. Given certain scenario, you have to take yes or no. Okay, with exactly one input x star, that satisfies f of x star equals to 1. There is only single solution. That means if you have a binary bit string, for say for example, it's a string of certain numbers, and you don't know whether they are for example, they are unsorted array, and you want to just calculate the maximum or minimum of the number. There is single maximum or single minima in that particular problem, right? So there is only a particular input x star where you satisfy the condition f of x star equals to 1. So classically, basically, classical solution takes order of 2 to the power n, right? So typically, instead of this big O notation, they often denote by this small omega notation, 2 to the power n, by classical complexity, to basically search the minimum or maximum of a number of particular numbers with n bits. Okay. Now, if you use the Grover search algorithm, for Grover search, you need certain things. For example, you need an oracle. It does certain kind of reflection and rotation, right? So there is something called Grover operator, right? So there is one Qiskit tutorial also, if you are interested to implement the Grover's algorithm. So you can do that up to certain number of qubits. So it takes only order of square root 2 to the power n, and this 2 to the power into square of 2 to the power square root of 2 to the power n is something called a quadratic speed up. The full scale implementation of Grover's algorithm for real time problem, like huge data set, will require large number of good quality physical qubits or good quality, number of good number of the logical qubits or good quality physical qubits. So for which we need to wait, and this is why actually Grover's algorithm is called a fault tolerant quantum algorithm, FTQC-A, fault tolerant quantum computing algorithm. A third one, of course, like Janani already told, like she discussed about the source factorization algorithm, source factoring algorithm. So the source factoring algorithm main fundamental is the quantum Fourier transform that finds the order of the number. I have a detailed 2-3 lectures on the quantum Fourier transform. Yesterday, I gave my website. If you are interested to see how actually source factoring algorithm works, right? And this is the fundamental part where QFT is basically find the periodicity of numbers or the frequency of numbers in the prime number factoring part, and that gives you the benefits of the computational advantage. There are two parts. One is the like QFT part in source algorithm, another one is the modular arithmetic. And this because QFT can be done in polynomial order basically complexity, and this is the classical post processing part, just a smaller thing like finding the GCD of numbers, etc. But in general, this is poly n. In fact, it is nearly order of 2 to the order of most likely n to the power 3. Okay, so it's a polynomial complexity with number of qubits. So if you have a 2048 number of say RSA key, right? You need to break this thing, right? So that means you basically need how many number of good quality qubits you can check. This board creates a problem every day. Just few seconds. So how many qubits we need basically for this particular problem, right? So 2048 is something like 2 to the power 11 most likely. 2 to the power 10 is 1024. 2 to the power 11, right? So suppose you represent 2048 bit numbers with 11 qubits, say n equals to 11. But the order of complexity is 11 to the power 3. That's quite nearly, I am not computing the numbers, but it's a huge number, right? 11 into 11 into 11. So let me calculate in the calculator. So 11, so 1331, right? So in general, now it depends on which encoding scheme you use, right? So this is the order, right? We can see now 2048 is a big number. In general, if you go for like angle encoding technique, for example, to encode the numbers. So this number is huge number, right? If this is the amount of like key you want to detect, like because there will be permutation, combination, and many other factors. So for which the total requirement of qubit, whether it is in polynomial n, and total gate complexity that is in polynomial n, because gate complexity part we are pretty sure like from the order of n to the power 3. But depending on the encoding scheme, like what is the number of qubits requirement, and accordingly, this particular number of gate complexity is going with the coherence time within the qubit fidelity or not. That's the question, right? So that's why this kind of algorithm only can be implemented in when we have sufficient number of millions of good quality qubit or in thousands of logical qubit. So logical qubit means, for example, if you have physical qubit, for example, right? So physical qubit means what? So you prepared a quantum state gate psi, right? And it may have error, right? So you represent by density matrix rho. Yesterday we have defined it like sum of pi, the sigma I and sigma I outer product, right? This is just how we defined it. Now suppose you have a composite system, like you have multiple such qubits, right? So Q0, Q1, Q2, and Q3, multiple such qubits, right? And these qubits are erroneous. There are factors like temperatures, the quality of the qubits, etc., for which they might be erroneous in nature. So if they are erroneous, what is happening? Suppose you are transmitting certain information from, say, here 0000, right? From the TX part, transmitter part, and in the receiver, suppose you receive 0001. So last bit, there is a bit flip error, right? Bit flip error. That means somehow, suppose I use 2 qubit to represent this phone number, Q0 to Q1. So I'm just, suppose it's a classical bit of information, for example, instead of gate, I'm just writing the classical bit of informations, right? And this qubit Q0 and Q1, they have four possibilities, like 0001, 1011. These are the four possible state they can create, computational basis states, right? Now, one of the basis states, suppose I got certain error. Suppose that means there is some bit flip error channel, right? Bit flip error is there. So for which basically the bit has flipped here, right? Bit flipped here, and I got an error, right? So that means when I will have multiple such qubits, right, and they might be erroneous in nature. So I need error correcting code. Error correcting code. So one of the code, for example, the repetition code. Repetition code is like this. So for example, name the qubits like Q0, Q1, Q2, and Q3. For a particular Qi ith number qubit, suppose I create, instead of one, I create multiple such for Q3, multiple such basically qubits I associate Q1, Q2, 3, Q3, 3. Suppose 6 qubit I take like this. Q3, 4, Q3, 5, and Q3, 6. So Q3 particular qubit, I have taken 6 qubit to corresponding to a particular qubit, right? And they might be erroneous in general, right? Now, this qubit supposed to be at gate 1 state, right? And out of, say, I measured this for 1,000 times, right? And I get basically for 1,000 measurement in these 6 qubits, I get 5 of them are giving 1, gate 1. Let me, suppose 5 of them gives me gate 1 with high probability, right? And only one gives 0, right? So majority is giving gate 1 for this corresponding Q3 qubit, right? So I'll take majority vote, right? So this is called the repetition code. Like I repeat the physical qubit in a way such that I take the majority vote of a particular quantum information. And if it is giving gate 1 every time out of say 1,000 or 1 lakh measurements, right? And then basically I take that particular information as the correct information. So this set of many physical qubits together with the error correcting code is called a logical qubit. Okay. So I mean, this is one of the very basic error correcting code. There are lots of theories like surface code, Gauss code, and there are many other codes. So now the question is again, um, we are talking about the complexity part, right? So if we have millions of physical qubits, and if you have good quality quantum error correcting code, which is equivalent to some several thousands, several hundreds or thousands of logical qubit after doing the correction, right? So we can create a quantum computer, which we call the fault tolerant quantum computer, FTQC. And source algorithm is one of the FTQC algorithm. Grover's algorithm is one of the FTQC algorithm. Quantum Fourier transform is one of the FTQC algorithm. Quantum phase estimation is one of the FTQC algorithm. Harrow-Hassidim Lloyd for linear system solving is an FTQC algorithm. All they need good quality qubit, logical qubits. But this doesn't preclude you to solve other problems, right? So there are other problems which people solve it. So all they belongs to some sort of, right, poly in either in qubits or in the gate complexity order. So typically we look for the gate complexity part, right? Let me take a new page. So this is the part for BQP class, and we'll briefly introduce a new class beyond syllabus that is called the QMA particular class, which is called the quantum Marlin Arthur complexity class. So basically it's an equivalent NP class in quantum, right? And it has also like we studied like NP hard, NP complete. Similarly here we have QMA hard, QMA complete, etc., right? So classical complexity theory classifies problems by resources needed for deterministic or randomized computation. Quantum complexity asks the same question for quantum computers, um, which problems like quantum computers for which problems are efficiently solvable, verifiable, or interactively proven when the computational power is quantum. So what is the QMA class? So the quantum Marlin Arthur class is a language. L is in QMA. We say it's a quantum Marlin Arthur complexity if there exists a polynomial time this is important, verifier. I'm not saying solver, I'm saying a verifier. So there is a polynomial time verifier which can verify whether the solution is correct or not, which is a polynomial size quantum circuit. Verifier itself is a quantum circuit, it's not a classical logic. It's a quantum circuit itself. And a polynomial Pn such that I say if x belongs to L, there exists a quantum state gate W, which is a verifier basically, or quantum witness. We call this as witness or verifier, quantum witness, because it's itself is a quantum state, okay? Such that the probability of the verifier V given the input X and the witness W that accepts is greater than equals to 2/3, or if X does not belongs to the language L, there exists some W such the probability of the verifier V given the input X and W as witness, it accepts with probability less than equals to 1/3. The verifier V accepts the input ktex and and get W as the verifier and runs for a quantum computation to decide whether to accept or not. Now I'll show some examples of this particular class, but before that, let me summarize with previous complexity class with the QMA class, and then we'll see a couple of examples and why the QMA class is very, very important for this near-term quantum computing, why we are using it, right? So I'm making a table, class, verifier, and proof or witness. So we have studied about the NP class, right? Non-deterministic polynomial class belonging to the NTM, right? Non-deterministic Turing machine, where you have a deterministic verifier, which is polynomial complexity. The problem is in NP, but the verifier is in polynomial, right? And you have a witness that is the classical string C. Classical string C. That is the verifier. If you have MA class, Martin-Arthur class, classical Martin-Arthur class, you have verifier, which is probabilistic verifier, which is BPP, bounded error in polynomial time complexity. And the witness is classical string. If you have QCMA, QCMA is a special class, basically quantum classical Martin-Arthur class, where your verifier is quantum BQP. Problem is in QCMA, but the verifier is in BQP, but your proof or witness is classical. See, now the ultimate class is QMA, quantum Martin-Arthur class, where you have both the verifier and the witness are quantum. Means if you want to verify the algorithm, you need a witness that is also quantum, right? So there also we have certain things like QMA complete. I'm not, because of time, I'm just stopping these details of the QMA complete and QMA hard. So these are equivalent to NP complete and NP hard, like that kind of things you can compare. Right. The first example is called the local Hamiltonian problem. So this might be helpful for the community joining this course from physics and chemistry. There is a lot of problems from physics and chemistry in this class. So the first one is called the local or K-local Hamiltonian problem. This is a QMA complete problem, basically. This is the class of the problem. So what is the problem? Given n qubits and m Hermitian operators. Now you can ask me why I'm taking Hermitian operator, because the eigenvalue of the Hermitian operators are the real, and all the physicists only, they prefer real quantities like positions, momentum, energy. That's why the corresponding observable is the Hermitian operator, right? So m Hermitian operators, H1, H2, Hm, is acting on maximum k qubits or less than equals to k qubits. There is a condition that with the norm of this each individual Hamiltonian, local Hamiltonian, should be less than equals to 1. And there are real numbers. We have two real numbers, A and B, where A less than B, with B minus A greater than equals to 1 by poly, with the number of qubits polynomial n. And we can represent the bigger Hamiltonian as sum of the local Hamiltonian problem. I'll show example in the fermionic configuration, orbital configuration. So H equals to sum of I equals to 1 to MHI. This is the thing. Now what we have to do, we have to decide, given this configuration, that you have a bigger Hamiltonian, which is a sum of smaller Hamiltonian subject to this constraint. Decide, is the ground state energy of this particular Hamiltonian, I mean the quantum phenomena, lambda mean of the Hamiltonian minimum eigenvalue is less than equals to A, or is lambda mean of H minimum eigenvalue is greater than equals to B. Which one of these particular cases will be true? Either one of them might be true. So if it is A, if it is B, this is the threshold energy value. Whether your minimum eigenvalue is like this or like this. Right? This we have to design, which is the minimum eigenvalue of that particular problem, minimum energy state, right? To answer this question, there is something called a Kitaev theorem. I will not prove the theorem, but this is an important theorem. Kitaev's theorem. And it states that the k-local Hamiltonian problem, the k-local Hamiltonian problem is QMA complete problem. That means it is in QMA as well as it is QMA hard for k greater than equals to 2. Initially, it was proven for k greater than equals to 5. Later, it was proven for k greater than equals to 2. So to basically know the proof, I'm giving a reference by the title of the paper is QMA complete problems. Author name is A.D. Pukas, who is an MIT prof, published in 2014. So volume number 14, number 5 and 6. So you can just give this title and author's name, you'll get the paper. Like there is a detailed discussions of the Kitaev theorem to prove it basically. So this problem is a QMA complete as it encodes any quantum computation into a static physical system. It serves as the quantum equivalent of the Cook-Levin theorem for NP completeness. And let us take a more realistic example to understand this. First one example we'll take electronic structure problem. Electronic structure problem. So in electronic structure problem, basically our objective is to find the ground state of electrons or fermions in a molecule. Okay, so given certain Hamiltonian, which is a sum of local Hamiltonian, for example, let's take a molecular Hamiltonian problem. Right. So say H equals to minus sum of I equals to 1 to n half of half of this delta operator square. So this is sometimes called Nabla operator. I equals to 1 to n, j equals to 1 to m, Ri minus capital Rj. The small r are the radius for the like distance from the particular nucleus to a particular electron and distance from nucleus to nucleus, capital R. Okay. Plus sum over I less than j to n 1 by Ri minus Rj. So there are three particular terms I have considered. First term is called the kinetic energy in the system. Kinetic energy. Now, kinetic energy, you typically in Born-Oppenheimer, if you take the Born-Oppenheimer approximation, you consider that basically the the movement of the electron is as fast as compared to the nucleus, and also the basically nuclear is not moving as such, right? So you are basically disregarding the kinetic energy of the nucleus, only considering the kinetic energy of the fermions, like electrons, right? But typically, when your nucleus is moving and everything is moving, you can consider both part as well. The second part is electron nucleus attraction part. Electron nucleus attraction part. And third part is basically electron repulsion. Right. So if I have, this is a QMA complete problem. So what is interesting is that suppose I want to compute the ground state of this particular configuration. So now you can ask me, what is the relevance of this particular problem? Say you have a DNA structure, right? Okay. Now and it may be DNA, or it may be simple loop RNA, for example, right? Now, this RNA has a particular chemical orbital configurations, molecular Hamiltonian, or this particular DNA maybe it may have a particular molecular Hamiltonian problem, right? This RNA, suppose it attacks your body, right? A normal cell, right? So what is the minimum amount of energy if it gets is basically starting the protein synthesis, for example, okay? Or this DNA basically try to replicate, right? So this process has a lot of understanding, not only just the example of biology, but also suppose you have a particular structure, okay, aromatic structure, say for example, it may be certain particular chemical configurations, right? So what is the ground state energy of these particular configurations, right? So this ground state energy gives us a lot of insight about the molecular stability, reaction dynamics, etc. Right? Now that's why these are important actually, because for example, you have certain molecule, you need to understand, okay, what kind of heat I need to give it to get a particular a notion of the things, like what is the minimum energy you should give in a particular, say for example, the ice, right? So that it start melting, right? Of course, we know 0 degree for simple H2O molecule, but in case of say nitrogen gas based thing like cryogenic setup and all, so the setup is quite different. So there are huge example of ground state example like energy calculations, and there are a lot of applications in chemistry. And these are all set of QMA complete problem. And if you have a M orbital configuration for a particular problem, and if you take simply two body case, like it's not a many body case, but just a two body fermionic configuration with second quantizations, for example. So you have order of m to the power 4 number of terms. Now, if you have like exact solution is very difficult. This is also like when I say two body with certain quantization level, that means it's an approximation. Specifically, if you try to solve the complete picture, like that is a QMA hard problem, and in that particular case, without all these assumptions, you have M, C, N, M combination C, N, like M, C, N, M combination of N basically thing, like in particular fermion with M orbital configurations has this much dimension of the Hilbert space. For the full full computation, exact calculation basically. So this is like the approximate one. And this is like if you want to do the full computation, like full or exact computation if you want to do. So of course, this is equivalent to order of like EXP, exponential complexity with order of the M, right? And typically the chemistry people, like the chemists, they do in classically they do the UCCSD theorem, or UCCSD particular answer based solution, or the full configuration recovery FCI method. These kind of methods they typically apply. And they have checked that if m is less than equals to 50 number of orbitals, we can quite calculate quite good for the chemical molecules. But there are molecules like, for example, biomolecules, various aromatic compounds, very highly reactive molecules, or the basically radioactive molecules. It is very difficult to identify that the ground state calculation or the excited state calculations, right? So people are working on the quantum algorithm as well. For example, VQE, light VQE, variational quantum eigensolver, kite algorithm, quantum imaginary time evolution algorithm, kite algorithm. Okay, these are some of the active research area just to push this boundary. Like, can I go beyond 50 or not? This is the question, right? So that I can basically calculate the ground state with more accuracy terms, etc., without explicit approximations, right? The second set of problems, so this is the one set of problem, and the second set of problem is I'm not going the detail, that is called the quantum phase transition problem. So many people are working on the first problem, like especially the cultivation of science, Kolkata, IIT Bombay, IIT Madras, ISC. So we have a recent paper on this a particular algorithm called sample-based quantum diagonalization, so which is a quite advanced quantum method. A lot of things we have been trying on bigger molecules with IIT Bombay. So if you are interested, I can share our archive paper. And the second set of problem is called the quantum phase transition problem, where suppose you have a given particular Hamiltonian H, right? And it has, say, the minimum eigenvalue is lambda 0, and the basically first excited state is lambda 1, right? So if a Hamiltonian has a spectral gap or not, that means the spectral gap is lambda 1 minus lambda 0. Suppose we take the modulus value, okay? To check that whether lambda 1 minus lambda 0 is greater than delta, or lambda 1 minus lambda 0 is basically less than equals to small delta. So if delta greater than equals to some epsilon, we say it's a gapped material. Or if the spectral gap is very less, like delta is less than equals to some delta, is a very small number, so we say it's a gapless material. So this study is very important in basically studying supercapacitors, superconductors, etc., various material science, etc. Okay, so this is also another QMA hard problem or QMA complete problem basically. And in general, the relationship is like P is a subset of BPP, is a subset of BQP, is a subset of QMA, is a subset of P space, and is a subset of EXP, exponential complexity. So currently, we target quantum algorithm in the BQP class, but there are problems in quantum chemistry, quantum physics. Probably you can bring more problems from quantum engineering aspects. For example, you can ask me some communication system problem, because today I had, say, communication engineering problem. Now, communication engineering, you are basically transmitting a lot of signals from here, lot of received signal from here. And say your transmitted signal is X bar, there is a channel H, and you have a reception Y, right? Y equals to H X bar, and you have some noise, basically distribution W, right? Now, whether you want to estimate this X, right? Whether you want to estimate the H head, right? Channel estimation, you want to detect the data, like data detection, right? Depending on the length of basically what is the number of bits, n bits data you transmit. Now, if you want to basically estimate the channel, if you want to compute detect the data, right? So these are the various problems we do in the wireless communication system. Now, what is the complexity order of this problem? Whether it's a polynomial problem, a polynomial with bit string, or exponential with bit string, or what, right? So that kind of problem you can think whether it is coming under BPP, BQP, QMA, P space, where, right? So typically this BQP is the set of problems where we look for quantum advantage. There is no guarantee, like QMA is equivalent to your NP problem in classical. So there is no guarantee that P equals to NP. This may not be the case. There is a millennium price, right? So we don't know whether a particular problem we solve in QMA that is giving quantum advantage or not. But in general, whether we can solve the same problem on a quantum computer faster or not, even if it is not in the order of complexity, but whether we can solve that it faster or not as compared to the classical part, that is a question in the QMA, right? So these are various aspects when we design algorithm, and I think I covered most of the important computational class. When you design next time quantum algorithms, you can keep in mind what complexity class I am solving the problem, and some notion in the broad picture, right? Why I am sitting in the bigger picture, whether I am giving polynomial advantage, exponential advantage, whether the advantage word is clarified or not, just I'm saying advantage or supremacy. So all these things, theoretically you can validate, or experimentally you can say, okay, I am giving this much time benefits, time complexity part. That means minimizing the number of quantum gates, improving the coherence time, etc. So all these things all these norms of the quantum informations are relevant to the complexity theory. I think I have merged multiple units of my across sessions in 10 lectures. And here I give the flavor of complexity theory, various examples from physics and chemistry and biology, as well as engineering, like the communication control engineering. I tried to connect each and every term using mathematical, basically formulations, as well as the underlying quantum physics and quantum information, basically in general, right? So there is a multiple flavor of things. Yeah, I hope you enjoyed the session, and you all feel free to ask me any questions. Thank you very much. Is there any question or something you may please put in the chat box? I'll be sharing the notes for today and yesterday. Rest of the notes I shared already. Was this session boring or something? Like any feedback regarding the session? Sorry, I couldn't write everything because of time, and sometimes my whiteboard was creating problem. Other than this, what is the coherence time of IBM hardware? Okay, in IBM hardware, basically IBM machines, we have the T1, T2 times, right? Coherence time. So they are of order of some milliseconds. Sometimes it's few microseconds, some 100 microseconds. So each hardware has different noise figure, coherence time figures. Let me quickly check the IBM cloud and come back with an answer with the latest hardware we have. Right. So let me share my screen. So this is like you can create an account in IBM cloud platform. Okay, the address is, I hope you can see my screen, right? So you can choose a device. There are many, like list of many number of device. So for example, I choose the IBM Kingston machine, right? You can see there are 156 number of qubits. There are many couplers. What is coupler? That connects one qubit to other qubit using certain waveguides, etc. You can see the 2-qubit error and 2-qubit layered error from left to right when you cross the circuits. There is a metric called CLOPS, that is circuit layer per operations, like flops in the classical qubit. I talked about the basis gates, right? How you represent your quantum circuit in terms of the basis gate. Here CJ, ID, RJ, RG, RGG, SXX are the basis gates. Then you have asked about the coherence time T1, T2, like 266 microsecond and 142 microseconds for the Kingston machine. This is the qubit topology map of IBM Heron processor. This is a heavy hex encoding scheme. So just from live, I am showing those who are interested, you can create an account to IBM Quantum Cloud using your student ID or faculty ID, institutional ID are preferred. I'm putting the IBM Cloud link here. Yeah. Yes, sir. Sorry.
No problem, sir. You can answer. Any papers for latch biscuit?
Any paper where it is?
Arunima Kumari ma'am, is the screen visible? Of course, anyway, now you still
I
go.
just stopped screen visibility. Sir, can you share the papers for latch D Qiskit? What is that? I did not understand the question. For Qiskit, okay, I can share the Qiskit tutorial. There are lots of Qiskit tutorial. Although this session is not for Qiskit, but I can. Okay, I'm sharing the Qiskit tutorial link as well in the session here. Yes, sir. So mostly done, I think.
Yeah,
okay,
thank you.
Yeah, there is a D-latch part. This is digital electronics things. So this is not part of the course, but yeah, I'll share some notes. I mean, I don't have personal notes. I'll share some online resources to Pillai sir. Yes.
Sure, sir. Thank you. Yeah, last question, sir. You can take.
Yeah, any guidelines for formulating or identifying problem statement from my office, use cases from quantum computing, especially optimizations and simulating kind of problem statement. Yeah, we discussed about the max cut, right? Max cut problem. There are lots of graph problems. In fact, those who are coming from computer science, there are lots of graph problems day to day, right? And you can use algorithm like quantum approximate optimization algorithm in the QBO formulations, right? Those problem you can easily try on current quantum hardwares. People have been trying on the quantum machine learning stuff as well for various image processing applications like image filtering. I mean, there is no guarantee that you will get an advantage immediately, but you can explore this kind of problems. Image segmentation, image classification. So there are lots of tutorial in Qiskit as well on this various image processing problem. For example, the cancer image classification problem. Yeah, I just shared the IBM Cloud link above. You can scroll the chat box and you will get it. Yes. I don't have like I haven't worked on the D latch or these kind of things like buffer or anything. I haven't come across any paper so far, but I mean, if I get something, I'll share surely. Yes, sir. You are not audible, sir.
Yeah, we are discussing something.
Oh, sorry, sir.
Yeah. No problem. No problem. Yeah, thank you. Thank you so much, Dr. Mustafizur Rahman, for the concluding lecture today. And sir has taken a lot of time. He has taken, I think, 12 lectures he has delivered, or 10 lectures, I think, in all. That's almost 1/4 of the course. Thank you for the time coming from industry and also a quantum researcher giving so much time, and also the passion with which you teach is exciting. We are sometimes very humbled to see your commitment for material, notes, questions, everything on time and on schedule, and giving so much time in spite of your academic load and industry load that is there and your challenges. Good thing to see is he's a avid researcher and also published in a Nature. Nature is a kind of a journal which is the world's best journal, you can say. So he has recently published last year in 2025. So that is one thing. And then secondly, he has what do you say, authored a book, Cat 0, Cat 1. So most of you can get a copy of that. It's very affordable. I think less than 500 rupees. So that way, he has contributed a lot in the whole lot of these series. At least every session, every series, I think 9 series we have completed, 9th QT-09, and he has taken lectures in every this thing, and he is also delivered well and well received. So that's why we thank you so much. We're just waiting for people who are willing to join. Academies phase 2. Can you just rename which place academy, EICT Academy? So regarding notes access is not there. We are trying to build a MOOC curriculum kind of thing. It will take some time for the slides to be available. But the videos are available, which you can actually read. The entire notes will be there. But the slides is what is missing. I'll see, sir, what best I can do. Prahlad Rao, sir, I will try to do best. Whatever best I can do, I will try to make it available. So we will conclude this series. Series, this will be my last in this series. I've been part of the 5 this thing that is there. 5 quantum series I have been part of. Saula sir is our chief investigator. He's there. He was there in the inaugural also. And then
thank you.
Thank
you very much for supporting us. Thank you.
And Professor Vineet Savala sir is our chief investigator of the EICT Academy at MNIT Jaipur. So this program is conducted under the E&ICT Academy. He's a professor in electronics and also our dean here for digital infrastructure services. Yeah, and then there are 6 other academies which are there, except Warangal. I think all the 6 academies have joined. Jabalpur, TIPREDIM Jabalpur, IIT Kanpur, IIT Roorkee, IIT Guwahati, NIT Patna, and TIPREDIM Jabalpur. So that is 6 academies have joined. So you are all part of that. So that's something which we can look at. These again, these 7 academies have a convener. So sir is also the convener of that committee. So we'll be meeting hopefully on 7th. We'll be meeting for the AICT also, and also our project review meeting is also there. We are going to have that meeting shortly. So we are just waiting for other resource people or somebody to join. Maybe I'll request meanwhile to conclude. We'll just request Saula sir to say a few words. In conclusion, he is also the joint principal coordinator. Actually, I requested sir to be the principal coordinator for QT-09. What happened was sir made me the principal coordinator, and sir is the joint principal coordinator. So we'll start with few words, and then if there any speakers will join with us, we can share some thoughts. Sir, over to you.
I think first it's my duty, and on behalf of all CIs and Dr. Pilli also, we are really thankful to all the speakers. Especially today, we have Professor Mustafizur Rahman, who has actually supported us all the way for many of the programs. We are grateful to you, Professor Mustafizur Rahman, sir. And thanks to all the participants who have actually taken so much enthusiasm to learn various aspects of quantum. And I understand that out of this 9th series, the participant here, I think more than 500 would be actually would have done more than 5 or 6, as I understand that way. So it's a great enthusiasm from participants from all the walks of life, faculty, students, industry people. We are only humbled to present to you the series up to 11. And we are again thankful to all the speakers who have been actually unconditionally supporting our this effort to spread. So we are in between just facilitators, and we thank that way. We also thank our joining us in organization of these programs, various academies, 6 academies. All my CIs there and all my colleagues who have coordinated this program, especially today, QT-09. And thanks to our director, Professor MP Padi Saab, because he has been quite a motivating force for us when we started this quantum series. It was actually been conceptualized, spearheaded, and you can say implemented by Dr. Emmanuel Pilli to the left of me. And the shape we see today, we were just afraid to reach to what picture we have been seeing today. And we are happy that our efforts have paid. Thanks to him for like unstoppable kind of energy, and a lot of energy has gone into other parts of the other facets of the program, where he has to interact with ICT, with NPM, DST, many other institutes, and especially when we are happy to have Andhra Pradesh as a whole state joining us for benefiting from these programs. So we are with every step of development and growth of these programs in terms of learners joining and speakers supporting. We are every step, we are humbled with every step going on that way. So please keep us joining for next of the series. And thanks again to all the speakers, and especially Mustafir Rahman sir. And if you want to have some concluding remarks, please go ahead. Thank you all. Thank you very much.
I think, yeah, we will have a few of our participants also sharing. After Mustafizur, I'll request Anil sir also, if he is there from AP State Council for Higher Education, to share a few words. Then we will give time to participants. You can raise your hands. We'll give you time to share your feedback. I'll also request Prahlad sir, if he is there, Prahlad Rao, Prahlad sir, BB Prahlad. If you are there, you can also share a few thoughts. Of course, one thing I want to share is that this course is basically engineering foundations to quantum computing, which is like a revision of what is needed for computer science. Actually, this is not a full-fledged quantum course. Full-fledged quantum course, I would say, is Q2, then QT2, QT3. QT4 is quantum computation actually. QT6 is quantum communication. Then sensing and materials are the things. So those are the four major courses: Q5, Q6, Q7, Q8. Those four courses. So we finished actually that actually the what do you say, the cream of that content is over. Please refer back to the videos. But this is a course which you want to complete as a syllabus. What you and then, as sir is also mentioning, we'll repeat the cycle starting again. Maybe it may overlap with QT11 a little bit, so that the summer vacation is used. So we will announce shortly. So those who have missed those initial courses, you will get a chance to take that courses again. And somebody was also asking whether you will combine both the series and give the certificate. No problem. Any 6 courses that you do from this series that we have offered from MNIT or APSHE or other academies, put together the 6 courses, I think. If you do it, AICT will finalize whether 5 or 6 courses now. Once they decide, we will announce finally. So once you do that, then we will get that PG certificate. So don't worry. So Dr. Mustafizur, we also have Dr. Kapil Kumar Soni. After Dr. Mustafizur shares, we will have a brief time. Kapil sir, please note the time is not much. So please briefly, you can share your experience and also your thing. First Mustafizur, then Dr. Kapil. Yeah.
I just forgot. Anil Kumar sir, namaskar. And thanks for joining us and bringing the whole AP state to us. Thank you very much.
Anil sir, are you there? Yeah. Okay, Mustafizur, you like?
Yes, sir. I'll not take much time. I already speak like I have spoken a lot. So in general, like I want to thank like IBM because I am belonging from IBM Quantum team. I want to thank RIKEN Quantum Information Center. I am a visiting scientist there. I want to thank SN Bose National Center, a visiting faculty there. So my experience in quantum is like diverse. I have been learning things. The motivation is that whatever be your background, there is a one space in quantum for you. That is the good part. But you have to keep pace. You have to be patient. You have to keep patience and you have to work hard. This is not just like a buzzword like AI, not like that. You have some input and you will get some toolbox and not like that. You have to spend time. You have to understand the technology, and there are lots of use cases. And this is the time of development phase. It's not like use phase. Like you have something, you want to put it and get the something advantage, not like that. You are part of the journey of quantum revolution 2.0. Like the first revolution around 1920-25, there was a lot of development. Like this century also we have been doing. Personally, with my experience, like I have a bachelor in electronics communication, so that means I have some touch with the computer science, some electrical engineering. My master's was in statistics, statistical signal processing. I have some good background in math in from masters from IT Kharagpur. And then when I took the subject for my PhD, like quantum algorithms, so I did not think much. I only saw what is the language of quantum computing. I saw it's algebra and probability. I said, okay, fine, let's take it and let's see. So like accordingly, I go ahead and then I just got the flavor of the subject that there is everything like all the subject has intersections there. As soon as you appreciate, you have the patience to you need to surrender your domain in order to learn new domains, right? So that's it. Like there is a lot of scope, and people have been enjoying by teaching. People have been enjoying by learning, and I am just part of the learning. This effort by NQM National Quantum Mission, and yeah, that's it. All the very best to every participants to this journey. Yeah.
Yeah, over to Kapil Kumar Soni ji. Yeah.
Okay, good evening, sir. Good evening, all the participants. So, from my side at the valedictory session here, just being a practitioner and a researcher in the field of quantum computing and algorithms, because I already pursued my PhD in quantum computing and algorithm itself. Okay, so the thing related to this course, because I conducted only one session, and that time I observed a very enthusiastic participants that time. The people were having too much eagerness related to learning, and the context related to the engineering foundation that we covered in this course. We really that is appreciate the design as well as the content finalized in this course QT-09, that is fully giving the strength for the further learning of the quantum computing and the technology that I am known personally, because these are the prerequisites that needs to be covered before learning or before proceeding to learn about the quantum technology. And the thing is that because might be you people may not be able to just convinced with the fact, like nowadays everybody is doing on a AI. Okay, like artificial intelligence is becoming as one of the powerful, that is the thing that everybody is thinking upon that one. But I used to call it that there is no such AI. Okay, there is actually a quantum machine intelligence. Okay, like we people being a human don't think like always in a deterministic way. We always remain with our mind with the probabilistic ways of superposition. Whenever at every moment of our life or every moment of our that is our life, we used to learn or we used to think accordingly. We used to think accordingly like in a probabilistic superposition of taking the decisions, and once in the favor of the desired outcomes we usually take the decisions. Okay, so the thing is that slightly we people are not moving for the development of the quantum technology itself. Rather it would be a perfect integration between the quantum and AI technology. Okay, so by the that is the outcome of this course, you are now feeling you may already feel yourself to be very comfortable learning the quantum computing, and further to be integrated with the quantum AI domain also. Okay, so from my side, I best wishes to all the participants for the further learning, and I must appreciate the efforts of the coordinators, Dr. Shubhankar sir and Dr. Vineet Shukla sir. They have perfectly managed the entire FDP. So from my side again, this is the end, and I wish you all the best for the future learning of the related to quantum.
Thank you, Kapil sir. Kapil sir was very much enthusiastic to teach, so we said you come on particular day. Then some other speaker came again. We moved, but he was very much happy to. No problem, sir. Whenever the slot comes, so finally when we could find that slot, he could take it, and it was well received because he tied the whole things together, and it became a very concluding talk kind of. So thank you so much for that time, right?
Thanks for
Ashwath
your
sir,
guidance.
thank you, sir. Dr. Ashwath, I would like to share. Anil sir, you're there.
Yes, sir, I am here. Sir, thank you very much, specifically MIT, Professor Emmanuel sir, Vinith sir, and resource person from Mustafa Rahman sir, Aswad sir, and also Soni sir from different academic also joined. It is really a wonderful initiative, sir, having a collaborative approach. It will definitely strengthen the future FDPs. Really, it is a great initiative. And I profusely thank the team MIT, AICT Academy for successfully completing ninth series, QT series 9th, and only 2 series are pending. Definitely, I wish that it will be more competitive when compared to the rest of the series, because many of our faculty across India, not only AP, across India now connected with the quantum technologies and quantum algorithms. And it's my pleasure to invite you all for the algorithm workshop that is to be conducted at SRM University in the background of Amravati Quantum Valley on 5th itself. So who are near to Amravati, maybe Vijayawada, Guntur, even people from Andhra Pradesh can join. It is a physical thing one, and we can also share the live link where the people from IBM and other resource persons, even Nick from US also coming, joining there. So it's going to be very important session, particularly in the background of the DST and NQM is opening the algorithm call. So from our state only, there are more than 84 proposals submitted for this NQM algorithm projects. So definitely that will help those who are already applied or who are very interested in the algorithm work can join there on 5th. So it is open invitation from our AP State Council of Higher Education. And I take opportunity to thank our chairperson, Professor K. Madhumurthy Garu, for his wonderful initiative and taking the lead in implementation of the quantum minor courses as well as major courses in all universities. And not only that, we are handholding the faculty and students as well simultaneously. Thank you, sir, for giving this opportunity.
Thank you so much, sir. I would like to inform that people who have completed more than 5 courses, 438 are from Andhra Pradesh because of the efforts of Anil sir. Out of 942 who have completed, I think there may be another 40, 50 from this course who may join this list of people who have completed 5 courses. We will analyze and we will send you the invite by Monday for the offline, so you can update this thing. So thank you so much. Ashwath sir, would you like to add something before we go to first we'll have Gurnath ji after Ashwath sir, then we'll have Dr. Prahlad Rao. Ashwath Babu? Okay, while sir is occupied, let's unmute Gurnath sir. You can unmute. Any ESIT Academy phase, can you mention where you are from? Which academy? Gurnath sir, please, 1 minute.
Yes, sir, please, sir.
Okay, I think they are set. Okay, sir. Gurnath sir, you can go ahead, please.
Sir, first of all, thanks to all academy because of their open-minded and open way of teaching us. It is an remarkable, because when I was joined 2002, even though in my institute they will cover up with this screen also, I mean Windows also. Now it is all open-minded, and whatever they know they are sharing all the teachers, and it is my duty to whatever I understood I should be shared to my student. With this approach I was joined, and thanks to Pilli sir, because of your smile and communicating to the others, it will boost everyone, sir, to be frank, open-minded. And I always fan of the Mustafa Rahman sir, because I used to take his name in every time, every class, whenever I teach to the student. That is there, and I hope sir will communicate to the my student Mustafa sir sometimes, at least once in a 10 minutes, once in a year at least. So that any induction program is there. 10 minutes given to my students, sir. My students are very happy, especially Mustafa Rahman. And special thanks to the Aswat Babu, sir. Anyway, my son is there, and I also associate with that Aswat Babu, sir. And I want to have my student with this triple IT Harvard, so that we have a good bonding, sir. And thanks to everyone. And special thanks to my wife. She also sitting with along with me. She's also physics lecturer in PU College, 10+2 government PU College. And we together learn, we together write on papers, and we together used to be write the quizzes. It is more grateful. Special thanks to her also, sir. Thank you so much.
Yes, thank you, sir. Sir was mentioning that quizzes to saath mein nahi dena hai. Anyway, that's good. Prahlad sir. Prahlad sir. ऊपर प्रहलाद सर सर्च करो. Prahlad sir, you can unmute and speak now. Prahlad Rao sir. Okay. Ashwat sir, anybody would like to also share feedback? You can raise your hand. We will unmute and you can speak. You can share your thoughts. Another 5-10 minutes we'll conclude. Yeah, I think 2-3 minutes. Ashwat sir, yeah. Ashwat sir.
Yeah. Good evening to all of you. Good evening to the entire MNIT team and the hub coordinators. I hope people can hear me. I'm sorry, I'm traveling. Maybe some background noise is there. So, irrespective of that, I want to ensure that I am there at least for a few minutes for the program. So, thank you very much, the MNIT and the administration, the team of PSR for opportunity for us. Even though I've taken only a couple of days for this engineering technology module, it's very, very important. After having the intro to quantum computing, the actual hardware technology is being introduced here. Probably the participants might have got some insight how exactly the quantum computing is taking place on a real hardware. There are little more things to follow with more of quantum physics or actual physics in the coming few modules. So people will get much more in-depth understanding of how exactly the quantum hardware works, right? Like some of you are very much involved. That shows the passion. Like one of the participants, sir, has mentioned, the entire family is into quantum. That's amazing. The quantum computing family. So likewise, we would like to see many more people into the field and get into the field and do the research and spread the word and spread the awareness on quantum computing. That is something very much needed, because we actually in India we started, I would say, a little late compared to Western countries. They're slightly ahead when it comes to quantum computing, so we had to catch up. And in some time, like coming few days, we may also have to cross them or go ahead of them. So that should be the target for us. So once again, thank you very much. It's a wonderful opportunity to learn along with the participants. We'd like to see in the coming few more modules. We'll have more interaction. So I would encourage the existing participants also, please look into that and just register for the next modules.
Yes.
Let's say some of them actually feel that they may not have the background to understand. Please don't worry. All the fundamentals required background also will be touched, even though if it is not mentioned in the brochure, right? All the resource persons are very kind and very passionate people. They raise a small question related to background, they will cover it up. At least not on that day, at least in the coming next session, at least they will touch that. So this is how things are going on with respect to this FDPs. Not like conventional FDPs where only strictly the content being projected is presented. It's not like that. We are little more into the depth and more detailed understanding is also could be done. So once again, congratulate all the participants who have finished successfully this module, and I would wish them for the future the new modules also. Thank you very much. I'll hand it over to the Philly sir.
Thank you, sir. Thank you, sir. I think thank you, Ashwath sir, for many sessions in this entire series. Gurnath sir, Prahlad Rao sir, yeah, you are unmuted, sir.
You're able
Yes, sir.
yeah, you're able
Yes,
to
sir.
hear.
Yes, sir. Yes,
Yeah,
sir. Please go
are
ahead.
able to, yeah. Thank you, Emmanuel sir, and your entire team. And this is really wonderful. It's a new area where I'm looking into the computer science. Basically, I'm retired from CDAC, and CDAC team is also working now in the quantum computing side, and especially a lot of all the resource people, especially Ashwath Babu, Kapil Kumar, Musawwir Ahmad, all the people here, they're taking special interest, and then the way they taught and all that is excellent. But only one suggestion is, for certain classes, you have given too many classes, like 12 lectures for Jay Kumar, and a lot of things are, again, we can cut short certain things, and then we can accommodate, because and also everybody, a small suggestion if possible.
Yes, sir.
Many people have shared your notes, I mean shared their slides and all that, but some people, the whole class, they were trying to write, and then there are a lot of problems on the notes and all that. We are a little bit of disconnected and all that, so maybe that one. But thanks a lot for this one.
Sure.
But
Sir,
I couldn't do. I started doing from Q6 onwards. So the basic ones, 2, 3, 4, I am not able to do it. I am interested to look into that notes or something.
We are going to offer again, sir. I'll see. We'll discuss personally, and I'll try to help you. Right?
Sure. I'll talk to you. Thank you.
Right. Sure.
Excellent.
Yeah. Thank you. Thank you so much. Dr. Sonali, ma'am, you can unmute and speak. Dr. Sonali Ridorkar. Dr. Chandrasekhar Vellanki.
Yes, sir. Namaste. Good evening.
Yes, sir. Good evening, sir.
Sir, we are very, very happy to associate with all your webinars, the web series on quantum computing, and we have enjoyed all the lectures. There is no doubt about it. And also, Dr. Kapil Kumar Soni has explained very concisely. Really, Mustafa Rahman, no exception. All are great, really. And Janani Madam, Nivedya, everybody. But you have got a perfect team of quantum computing facilitators. This is what we are very, very glad, sir. And also we are proud of that. You belong to our SVH. We have joined in the college in the 99, sir. And we have been continuing there. And we are so glad, sir. Dr. Pilli, sir. Thank you very much.
Sure.
And
Yeah,
it is nice. We will do up to end, sir. No problem. We have already registered for QT-10 and 11 also yesterday.
Thank you. Thank you so much.
Everything, sir.
Thank
with
you.
all our inspiration only.
Thank you, sir.
Thank you, Director and Vinit Savla, sir, and all authorities, sir. Really, we are associated with MNIT Jaipur.
Thank you, sir. Thank you.
Namaste, sir. Great of you. My thanks to one and all. Namaste.
Right. Namaste, sir. Dr. Sonali, you can unmute and speak. Dr. Imtiaz Ahmed. Mohammad Imtiaz Ahmed.
Good evening, sirs. Actually, it's a wonderful opportunity to learn about quantum computing, particularly coming from an industry background, which is not particularly related with computer science. And since being a computer science graduate, I really found this opportunity to be very all-inclusive. And the faculty out here really did a wonderful job. They actually introduced the concepts in such a manner that actually provided a holistic view of the quantum computing, what all is needed to be an expert or to be a researcher in this area. So it's a great opportunity, and I think that National Quantum which has been started. This is the way I think which will take this mission further. So thank you, Pili sir, and all the faculty who has provided us with a great opportunity to learn this new technology. And I wish all the best to the faculty and the administrators who are running this program. Thank you so much.
Thank you. Thank you, Mohammad Imtiaz. Dr. Venkatramana.
Yes, sir. Hi, sir. Good evening. Can you hear me, sir?
Is it Sonali, ma'am?
No, this is Dr. Venkatramana. Can you hear me, sir?
Dr. Venkatramana, sir, yes, we are able to hear you.
Sir.
Yeah, please.
Thank you, sir. Thank you for the organization. It's a wonderful way you are organizing, sir, every course. You are bringing a world-class faculty for a very low price, sir. Wonderful way you are organizing, and every faculty is a wonderful way teaching, sir. And this one, Muzaffar Rahman, sir, is committedly teaching brilliantly. And Aswad Babu, everyone, sir, wonderful. They are communicating in a brilliant way, sir. Thank you, Sahil, sir. All of us, our team NIT is in a good way. They are organizing, sir, everything. Credit goes to Pili, sir, is incredible. Continuously responding with a tireless person like that. Pili, sir, maybe a tireless person is continuously doing brilliant work. A great mentor, sir, you are.
Thank you, sir.
Thank you for the opportunity. Thank you, sir.
So, if it is Dr. Sonali is there, or EICT Academy Phase 2, you would like to share something? I think it is either IIIT Kanpur or Jabalpur, I think. So, yeah, Dr. Sonali, I think she is occupied. Yeah. So I think we'll conclude here. Thank you so much for joining for QT-09. And many of you have completed many courses. I think more than 5 courses. There are about 1,000 people, I would say. And one statistics I will read just before we conclude. That is about 12,008 participants. Apart from QT-09 till QT-08, 12,008 participants, 12,008 participants registered. 10,731, 10,731 have qualified and they received certificates. So we have prepared a list of these things also. So this is the list of names of people who have received a certificate. So that list is now become a big file. And 8,607 are faculty members. And most of them, I would say, they are unique participants. If you ask me, 3,300 people. 3,300 people are faculty members. But actually, the whole people who have done uniquely, if you see those who have not repeated, those who have done at least one course, there are 4,500 people are connected. So when we send an email, head count, if you take it, 4,500. When we send email, we send it 3 times. So because what do you say, the Gmail will allow only 1,500 at a time with mail merge. So that is what it is. And then many of them are PhD holders, like we see Dr. Gurnath, Dr. Venkatramana, Dr. Sonali, Dr. Prahlad. So many people are PhD holders. And that's a great joy that people are willing to learn and we are able to facilitate. Thank you all. And there are many industry experts also. Today also I received a message from somebody who is part of HDFC and they are part of this course. So I was so surprised, thrilled. Many PhD scholars, research scholars are there who are doing their PhD in quantum, but they are greatly benefiting from this course. So thank you all teachers and thank you all participants to keep the momentum going like this. And hopefully we'll shortly announce, as sir mentioned, we'll start the 3rd series. First series was MNIT series, second series was APSHE series, maybe, or we merged both of them now. Or the second full cycle, you can see, it will go for 1 year, starting from June or July, and then go up till next year, June or July. So that will be 12 months, 12 courses we'll try to schedule. We'll announce immediately within this month, we'll announce in a couple of days. Once the meeting with AICT is over, we'll announce and then we'll take it forward. and I'll share a personal mail for those 950 people who are qualified to do the diploma course or certificate course. So we will share that information or email. So all those who have questions, we'll form a separate WhatsApp group for that, so that we can have communication easily, so that everything can be cleared. And whenever you have any query, otherwise we are disturbing the the regular class. So we'll have a communication among us. So we'll see when you can do that. So thank you so much. And we are a few people whom I should remember and thank, because I think the next two courses I'll not be there as a principal coordinator. First is our director, Professor N.P. Padi sir, who has given us full free hand and support in continuing and doing all these programs, and given me a lot of time to spare and do all these things. The first thing. Second one is Dr. L. Venkat Subramaniam, who shared with us in this program with the reference facility. He is the brain behind it. Dr. Mani Madhukar he is the university relations person, and he is the one behind this program. He connected us with AICT, IBM, and all these things. So he bought all of these things on the same page, and from there we could take forward. So sometime I will introduce him when he comes, maybe sometime. Mustafizur and they all know him. So that's something which I wanted to share. And of course, Saula sir, who gives free hand for us to continue and do it. And many speakers who have given their time very impartially. As you know, we are charging less. You can also look at the honorarium is also very less, but they are committed because they want to see that this is taking the material very forward. So many people are reaching, so that's why they are all, and they are giving the material, they are giving the notes, they are giving the video recordings, they are permitting, because everything is copyright actually. But then they have not asked for any additional this thing. So that's a great thing, and we are giving everything free. So that's the facility, and hopefully we all make best use of it. Anybody who wants, please ask them to go to YouTube, search the title, and they will get the material. We'll arrange the schedules and content. We'll put up a web page where people can directly go there, click, and go to that video. We are doing that. We are slowly working on that. So that anybody who wants to do any particular topic, he can quickly go and do that. So we'll set this up in the coming few days. Thank you so much for all of you, all the participants. You are there. 300 of you are still there with us, even at this time. So a big thank you to all of you, and thank you all.
All the speakers, all the participants, and
yes, somebody wants to say something.
Gurnath sir.
Yeah. Gurnath sir, yes, please.
सर मुझे एक कोट याद आ रहा है, इस मोमेंट पे मैं कोट करना चाहता हूं सर. टीचिंग एंड लर्निंग नॉट ओनली सेक ऑफ लाइवलीहुड, teaching and learning not only sake of livelihood, but also the welfare of others like teachers, but also the welfare of others like teachers. Serving humanity is serving God, sir. Thank you so much.
Thank you, sir. Thank you for that wonderful. Yeah, thank you all. It's bye from our side. Thank you for being with us. Yeah.
meet the next.
Thank you all. Best wishes to all.
Thank you, Kapil.
Thank you, sir. Bye.
Thank you,
sir.
Kapil.
Certificates will be issued.
Thank you, Dr. Ashfaq.
Next 5-10 minutes, you will receive the certificates. All the best. For those who have not completed, please complete it. Complete the quiz. It will be opened at 6 o'clock. So take the quiz, complete it, and Tuesday we will issue the certificates for the remaining. 445 of you have qualified. We are issuing the certificates in another 5 minutes. Thank you. All the best.
Thank you, sir.